the V1. Okay, and we span by alpha 1. Okay, and also remember that we can rearrange AV equal lambda V, and with this form equals 0. Okay, so we can write it like lambdas I minus A V equals 0, or you can write this way in A minus lambda I V equals 0. They're same. Okay, the same. But if we got this form, for example, and this is 0, it equals 0. So this is 0. This is, and we here we have vector v1 here, a vector. Oh, we can find vector v1, v2, and up to vn. Okay, if we got n eigenvectors, you can find n eigenvalues associated with the eigenvalues. Okay, and because all of these vectors have we got this is 0, or other words, this is a null space of this null space, the vector v. Okay, because this is 0. And in this example, we'll have also v2 like this, or you can write the v2s equal alpha 2, and here we got 1 minus 2. Okay, so you can combine two vectors like this when we got the vectors, a matrix of all eigenvectors is here v1 and v2, and it equals, okay, this is alpha 1, and this is alpha 2 minus 2 alpha 2. Okay, this is v1, this is v2. And you can find any value. For example, you can assume that alpha 1 is equal to 1, so this is 1, 1, 1 minus 2. Okay. Okay, and sometimes if matrix A can be transfers into the diagonal form, then you'll see that if we got a Jordan matrix, you can transform A. I can find any P, okay, and it equal P, okay, Z, P minus 1, okay, and in this form, you see that Z is a Jordan matrix, and you find in an example in MATLAB, you can check this and see that if Z is a diagonal form, you can find P in this form. Okay. I also give you an example for that. We got, I'm not sure where it is. Oh, this one, I think. You have also the example, and I'll practice on this. Find eigenvectors of this matrix. Okay, and you did this, and we find the solution of lambda equal 3 and lambda equal 5. Okay, here we got all this solution before, and because of that, you can construct the Jordan's matrix this way, because we have lambda equals 3 appear here in 2 times, and 5 appear in another root. It could be 5, yes. Okay. And you can find eigenvector for this. Okay. So you already see that if you apply in the first case for lambda 1 equals 3, you can find that you can find this. Okay. we assume that the vector v1 is like this. So you can construct all this. You did this, okay? And okay, we will see that this is v11 minus v13, and I can choose this is the base, and you can 5 v1 like this. Of course, the requirement is that v1 is not 0, 0, 0. So at least we got this one. Okay. And also we have to 5. You may 5 and because we have this is number 1 is 3, but in multiple. So in case we got a multiple root, we got we have to 5. Totally we got 3 eigen values. You may have to 5. If you would like to construct the diagonal form, you have to 5 P, a vector P like this, a matrix P like before here. Okay, so this is should be 3.3, 3 by 3. Okay, because we multiply this by this, and Z is 3 by 3. Okay, so if you have only 2 matrix, 2 vector like this, so we got, for example, 1. Okay, 1, for example, P is 2 vectors, so we got 1, 0, 1, 0, 1, 0, for example, like this. So you cannot use this. Okay, so we have to find more eigenvectors. But how? Because we have only 2, 3 root, but we have the multiple 2. Okay, so you can find another vectors, but in this case, because we have 2 repeated root, so if you find another vector, so they will so have to find another vector, but 2 of them will be dependents, not independent vectors. Okay. So it could be dependence, or in a lucky way, in a lucky case, we will got independent vectors, but in normal way, we will got dependent vectors. Okay, for example, now this. But how can we find another V? Okay, if you would like to find vector number V, number 2, okay, you can find that you can apply this. Okay, apply. But how can we find this? Okay, mechanically, we can read. I can look at the Jordan form. It's like this. So you see that if you got 3 like this, so you can see that you can base on this Jordan form to find another vector. So this is the vector number 1. It corresponds to the vector number 1, and this is correspond to the vector number 2. And here we see that at this point, we will see that V1, the V1 correspond here, and V2 here. So you see that this we have 1 here and 3 here, and mechanically we will find the vector number 2 equal to V1. If we got a vector number 2, we'll got a V1 plus this is the lambda 1. Okay, multiply V2. Okay, we can apply this. Okay, and if you apply this, you will find the V2 like this. Okay, so this is we just have observed the Jordan form, and I will explain if I have time on this next slide. I will explain why we got this. Okay, but it takes time because we don't need to check this. I said you can use MATLAB software to find this. Okay, find the second vectors like this. Because I put alpha 1, it will be expanse of vectors. So we can find any alpha 1. Okay. And because I put this form because when you MATLAB, you can find that it said this is maybe 0.7, okay, and 0, and you got minus 0.7, okay. In MATLAB codes, you will find it. In the MATLAB lesson, you'll find something like this, okay. And the first vectors, it doesn't matter, but the second vectors, it look like this. So you can see in this case, alpha 1 is 0.7. For k, lambda 2 is 5. Okay, it's normal. You can get this form. And finally get this form. Okay, so in MATLAB code, you will find the 0. Here we got 0.4. Alpha 2 is 0.4. And here we have 0.8 and here 0.4, for example, like this. Okay. So we have, you will see that we got V1 with, so we can contract P like V1 is 0, 1, 0, V2 is 1, 0, minus 1, and here we got 1, 2, 1, like this. So, okay, you can make sure that, okay, we have A is, because A is, I said A equal P, Z, P minus 1, or in other words, you can find that you can multiply here, we have the, or in other words, you can find that this will be Z equal, if we multiply P, A, P minus 1, AP, then this is a Jordan matrix, if you find this. So based on, you can find the Jordan, if you base on the transfer function and put it in the form of the sum of fraction equation of terms, or you can find the Jordan form if you find the eigenvalue and eigenvectors. Okay. Okay, so I have here, I put also remark on this. Why we got this? So we look to 0k, but not 0k. I put only 3 by 3 to explain this a little bit. So actually, we will see that we got this form, or in other words, you want this, you can got this form. If okay, or in other words, you can find this. If you find matrix M's and make this in the next section, you see that is a linear transformation, and it doesn't change the eigenvalues. Okay, and if you can find M satisfy this equation, or in other words, Z is Jordan matrix. So in other words, you can find that. You can find the Jordan form of this by multiply both sides by M minus 1. So we got M minus 1, A, M. Okay, so M is container of the eigenvectors of this. And I assume that M it can be represented this form. This is the first vector, this is second vector, and this is the last vectors. Okay, so this is M1. This is the M2 and this is the M3. Okay, and we assume that in the previous example you got lambda 1 repeated 2 times, and this here only lambda 2. Okay, so we calculate now. First we calculate MZ. So how it look like? We have M like this. How MZ look like? Okay, so we find that MZ is this multiplied by this. So we got 3 by 3, and got here also 3 by 3 matrix. Okay, so in the first column here, you see that this is correspond to the vector number 1, and here is vector number 2, and this is vector number 3. Okay, so you can see that this is the eigen, if you set that this is the eigen correspond to the eigenvector number 1, eigenvector number 2, eigenvector number 3. So we see that if A multiplied by M1 only, and take the first here, then we got this is a first vector V1 correspond to the vector V1 or M1. Okay, so this vector V2 that correspond to the next columns, it equal to this. Okay, so that reason why in the first here in the example you got vector V2 equal V1 plus lambda 1 is 3 V2. Okay, and so on. You got more, you can put this form. Okay, and so on. Okay, but I said you can do this or not, it doesn't matter. And after that, I will show you how can we calculate eigenvalues of matrix A. And you see that if you use eigens like this, you can, MATLAB will return for you V is eigenvectors, V for vectors, and D is diagonal matrix with a of eigenvalues. So in this case, for example, like this, and you got this one, V is this one is this is a V1 and this is a V2, and here we got a diagonal matrix, and we see here this is a lambda 1 and this is a lambda 2. Okay, you already don't know this. Okay, and after that, I will show you that eigenvalues and pole are the same. Okay, because we see that we know already that we got this one, and the transfer function can be represented this form, and this is a characteristic equation. And if we take this equals 0, then we got the poles, and also we also know that this also eigenvalues. So the pole and eigenvalue are the same. And also we've got the transformation of state variables. If we got a state X, we have the system represented in this form, but now we change X by X dot and we X prime. Okay, so we'll have P in like this. Okay, so we change from X to X primes. Okay, and we 5 eigenvalues of this. Okay, we represent re-represent the system in this form, and you got the system. It look like this. You would change the system state variables by using a linear transformation matrix P. Okay, then we got this is the new one. So we can put X dot prime equals A prime X dot plus B prime use. And this is A prime, and this is a B prime. And this is also, this is C primes. Okay, and now you like to calculate the eigenvalues, then you put eigenvalue lambda I minus I primes, and it got this form and this form, and finally we see that it equal to this. So this means that, okay, the eigenvalue doesn't change when we change from you do different state variables. Okay, but eigenvalues, it doesn't change with this. So that's the reason why we call this as a equivalent representation. Okay, or similar representation. In some books, they said this is also a similar transformation or similar representation. So one system we have many ways or many state space equation that represent this kind of system. Okay, so this is something we have been learned. Okay, so we'll apply all of this knowledge to the problem of decay when it look like we would like to push or locate the we would like to locate the pole at any point we want. Okay. And then we will investigate an example of doing this. Okay. So we call this, so you in the last lesson, that we will be called pole placement methods. Okay. So this is the concept of this. We assume first that all state variables are measurable and available for feedback. Okay, we assume that we don't need to design observers. And if the system considers complete state controllable, then the pole of closed loop system may be placed at any design location by means of state feedback through appropriate state feedback gain matrix. Okay, and only in case the system is completely state controllable. The state controllable means that we can, okay, put the state variable up at any point we want in a finite times. Okay, you can, okay, sometimes you can place a pole or eigenvalues or the pole of the system at any point, but the time is infinity, so it's not controllable because we have to the definition of this process, but in limited times. Okay, and we assume that we decide that the designs closed loop, we have to find the closed loop pole. We would like to put it into the position s equal to sigma 1, sigma 2, or up to sigma n. Okay. And now we have to find the state, the feedback gain matrix. Okay, to have this position of the state variables. Okay. And we assume that the system is single input and single output for simplicity, and the reference input is 0, meaning that we put all of this into the origins of the system, or in the place of 0, 0, 0 up to the n. And when the control signal is vector quantity, the mathematical aspect of the pole placement become complicated. Okay, because when the control signal is vector quantity, meaning that a multiple input, multiple output, okay, then the state feedback gain is not quite simple and not unique. Okay, but we will not consider this because this is very advanced topics. Okay, so we just have the need to know the idea. How can we place the pole at the design location? Now look at this. We assume that we got a system represented by this equation as a classical way. And already know that we will have the input signal in UEKX. I hope you still remember that form. Okay, maybe I will write here again. So we got, okay, we assume that we have the reference input here. And here we got B, and here we got A, okay, and this here we got integral x dot here. So here we got x, okay, c, and here y, and assume that all of x here can be available for feedback. So we will put, you can find this is minus k, or you can put k here, and then plus k. It doesn't matter. You put k here, then you put here is not okay. So this is u. You put here, and you have plus minus here, so it will be minus k. Okay. So all at here is available for feedback loops. Okay. Then you also I equals 0. So you have if I equals 0, so use here equal to minus k x, because this is x. Okay. So this is kx, and this is minus u is equal to minus kx. Okay. Okay, so this is like this. The matrix gain K forces the eigenvalue of this to be sigma 1 up to sigma n. This is the design notation. Can be summarized in this by this step. Okay. And remember that if any of sigma I is a complex eigenvalue, then its conjugate must also be an eigenvalues of this. And you have this in the eigenvalue section. We already have noticed about this. Okay. Okay. Now, I have. Okay, you can find out why we got this step in the books. Okay, and many books explain this. But here I just summarize how many steps we can do to get matrix K. Okay, to obtain the matrix K. Okay, so we have several steps to do that. Okay, so the step one. In a step one, we have to check the continuability condition for the system. Okay, if the system is completely state controllable, then we will use the follow step. Otherwise, well, we have to stop and said that, okay, we cannot do that. Okay, because the system is not controllable, completely controllable, so we cannot put any pole at any location we want because they are not controllable. Now we assume that the first step is the condition of the first step is satisfied, and then we can move to the step two. Okay, in a step two, we will see that we have to find the characteristic polynomial of matrix A, or in other words, this is characteristic equation. Okay, and of course, this is if you want, you can put it in this form. This is polynomial, or this is an equation. This is a polynomial of the matrix A. It's characteristic in polynomial, but you put it 0, this is a characteristic equation. Okay, you have to put this form, find this form. You already know how to do that. And it specifies, here I don't know, I update this, but I change a little bit. For example, in many books, they put A naught here, A naught Sn, and then A1 Sn minus 1, and up to here we got An. Okay, but as I told you before, I would like to have a consistent between the system 1 and system 2. And in system 1, I denoted in this form. And then I follow this, I update the slide a little bit. So now we have this form. Okay, so if we find the characteristic polynomial, you can put it in this form and know the coefficient is from A naught, A1 up to An minus 1. Okay, and then in step 3, we have to determine the transformation matrix T, or maybe P. Okay, I mean that transform the system state equation into the controllable canonical form. Okay, I hope you still remember that we got the form, the continuable canonical form. It can be represented in this form, which is 0, 1, 0, and 0, 1, 0, 1. And here we got a minus 1, it is 0, a minus 1, up to a minus and a minus 1. Okay, and B is 0, 0, 1, something like this, use. Okay. Okay. So if the given system equation is already in the continuable canonical form, then we can see that T equal to in unity matrix, meaning that we don't need to find this, because anything multiplied with the A minus in the unity matrix is the same. Okay, itself, even my I minus 1, even T minus 1. Okay, T or T minus 1, same. So all of the of this step is have to find matrix T. Okay, and in step 4, using the design eigenvalues and design closed loop pole, this is actually like this. Write the design characteristic polynomial in this form. Okay, and by this form, you can find alpha 1 and minus 1, alpha 1 and alpha naught. Okay. Okay. And then finally, we will find K by this form. We take alpha naught minus A naught, alpha 1 minus A1, up to alpha n minus 1 minus A n minus 1, multiply by inverse of the transformation matrix. Okay. So that's the reason why we need to have the controllable canonical form. Okay. So again, we have totally 5 steps. In the first step, we have to check the system, whether the system is controllable. And if the system is controllable, we'll move to the step number 2. In step number 2, we have to find the characteristic polynomial of the matrix. Okay. And in the next step, we have to find transformation matrix T, and we got to find the canonical controllable form. And after that, we have the design eigenvalue or eigen annotation. Then we find this. We just take the alpha s minus sigma 1 s minus. Okay, sorry. This is my 1, 2, 3. Sorry, I make a mistake of this. Okay. And we this is the location of the alpha sigma 1 as sigma. This is sigma n. Sorry. Up to sigma n. Then we got this is the polynomial of the characteristic polynomial or characteristic of the eigenvalues. Okay, and then we apply this to find the matrix gain K. Okay, and then we'll do this by using an example to understand the methods. Okay, now look the system given by this equation. Okay, so we got this is a matrix A represented in this form, a B in this form. Okay, and we assume that we choose the desired closed loop pole here. Okay, and okay, so I have to explain again Okay, that you if you got have no, if you have no k, okay. So in this case, u equals 0 because they have no k or k equals 0. Then we got this is 0. Okay, so u is 0. So in this case, we have no feedback loops. Okay, no feedback loops like this. So we have open loop system. Okay, so for open loop system, in other words, the system itself, you can find the this is a characteristic equation. You can find the pole of the system. Okay, but this is a open poles. Okay, now you close the system, close the fit with the feedback loops like this. With k like this. So the closed loop pole is the pole of the system itself, include the control k. Okay, so this is closed loop pole. So when we apply k here, we expect that the pole will be the closed loop pole will be like this. Okay, and again, remember this is a closed loop pole, not open loop poles. Okay, so we follow this step. The first step is check the system continuability. Okay, and you know how to check this? Okay, we have to check this using the continuability matrix C. Okay, and apply this. Okay, because this system is n by n and n in this case 3, so we can check with the a square 3, and we got 2, and got this one. Okay, and if you check this, you will see that we got this is the c equal to this. There's a c in this is a mass calculation. It is not c like this. This is Greece c. Okay, remember that it look quite similar to C, but it's different. Okay, so you see this is a C, the continuability matrix in like this. Okay, now we uncheck the determinant of this, and you check this. The determinant is -1, and the rank of C is 3. So meaning that the system is all of these vectors is independent. All these are independent, so the system is completely state controllable, and arbitrary pole placement is possible, meaning that we can put any this in any location we want. Okay, and now we go to maybe I have to put this is a step number 1. This is step number 1. Okay, and next we move to the next step. We have to find this. Okay, so remember xn n minus 1 up to a naught. So we move to say the step number 2. This is step number 2. Okay, you find this. Okay, we will have to take si minus a. Okay, and we will see this. We got this form. Easy. Okay, we will practice several times on this. And okay, we find this. So remember, this is a if we got a, so this is a coefficient a3. But as always, because if we put 0, so we can divide both sides by a3. So we as always, we got a's, the largest orders of the polynomial, always 1. Okay, so a3 in this case, if you want, we'll put a3 is 1, and here we have a2 is 6, a1 is minus 6, a1 is minus 2, and a naught is 1. Okay, so we find this in step number 2. Yeah. Okay, so we determine all of these values. Okay, now move to the next step. Okay, we have to find the transformation matrix T that make the A in the tunable canonical form. But this is a example, a very simple example. So I take the example very simple because I don't put it here. Okay, I didn't tell it here, but in the step 3, exactly 5. Step 3 is already because we got this form, the matrix is already in the canonical form, continuable canonical form. See, we have 0, 1, 0, 0, 0, 1, and this is this is in transfer function. This is a minus a naught. Okay, this is a minus a1, and this is a minus a2. Okay, so it already in also B is already in the continuable canonical form. You don't need to find this form. So because that T equal I. Okay, this is a lucky way, a lucky case. Okay, but of course, it depends the problem. Even for another problem is we got not this form, you have to find ourselves. Okay, and then we in the next step, in the step number 4, we will find the polynomial characteristic polynomial correspond to the pole we want. So we have to S minus delta 1, sigma 1, S minus sigma 2 up to sigma n. And in this case, we got okay, so this is sigma 1 is minus 3 sigma 2 here, and sigma 3 is here, correspond to this pole. Okay, so we will push polynomial is S minus S1. Okay, S minus S2, S minus F3. Then we will got this polynomial. And before we will see that this is alpha 3, but alpha 3 always 1 because we put 0 here. Then we will see that this is alpha 2, okay, is 12, alpha 1 is 47, and alpha naught is 60. And then the gain can be found like this. You see that alpha naught minus a naught, alpha 1 minus a1, alpha 2 minus a2, and this we apply this. Okay, so we already know that a naught a1, a1 is 2 minus 2. Okay, and a3 is minus 3. Then this is the case. Okay, so this is the gain, the matrix, the gain of the matrix K, like this. Okay. Any question, please?
Sir.
Yeah.
I just think about A2.
Yeah.
Why A2 equal minus 3? Because I see A2 needs to be equal 6. You can
A2?
Go up, yep. A2.
Yep. Yeah.
Minus 6.
Sorry. Oh, sorry. I make a oopsie, me here. Okay, 6 is not 6, it's 6. But maybe I am miss. I don't know. Yes, I will. Please check for me, please, because maybe I make something in the typing. Because this is it here. Maybe 3 minus 3.
Oh, okay.
Or it should be minus 3 here. I think you can calculate this. We will check it together. Okay. I think that I have something wrong here. Okay, we check. Okay, so we first start with this, and with this, so we got S. Okay, multiply by S minus 3 minus this A minus 2. Okay, determinant of this, and we start with this. So we got the -1, -1. So we have -1 plus -1, and plus the minus of this. So 1 minus 1 multiplied by 1, we got -1. So minus of -1, we got 1. Okay, and this is 0. Okay, because 0 here, 0 multiplied by the determinant of this is 0. So we got here, we got S3. Okay, so this is the -3S square. Okay, 3S square, just meaning that this is 3. Okay, and that's the -2S plus 1 equals 0. So finally we got, okay, this is also the finally 4. So please change this for me, this -3. Okay, it's not 6. Okay, so the result still correct. I have typing errors. I will update this later. So finally we got the gain of matrix like this. Okay, so I hope that you understand of this step. Okay, any more question, please? You have any more questions?
No, sir.
Anyone? Okay, okay. Do you need some break? Some minute of break? Okay, okay, good. Okay, after the break, I will give you another example, like this, okay, to practice on. And please do not uh, open the slide first. You will have to practice a little bit and find it yourself, okay? But okay, now take breaks. Okay, are you all here?
Yeah, yeah.
Yes, sir.
Okay, good. Sorry, I have something they have to show with. Okay, now we move to the next example. I think that I need to, okay, make another example. Even I didn't prepare for this, but it should be better if you find another example to practice in. Okay. So now assume that we have the same problem, but now we have to find um, the gain matrix, the matrix gain for the system like this. Okay, let me see where I can put it. I thought that I can give it just for you for practicing, but I think it already in slide, so it's not so good to do that. So I assume that you got this system. Okay, A equal 0, 1, 0, 0, 0, 1. And I also put it in a controllable canonical form for you, so you don't need to find the matrix T. Okay, and then we got here, for example, -2, -5, and -10. And B is 0, 0, 1. Okay. Okay. So we expect that we put uh, the first location of S is -1, Z1. 2 is, because this is complex root, so I have to put also conjugate S2 is -1 minus Z1. And okay, and finally S3 equal -5. Okay. Now practice on this, please. Okay, if you have any questions, you can ask me directly. And if you are finished, please share with us. Okay.
Sir,
Yeah.
can I share my screen?
Yes, of course. Please share with us, please.
Okay, here I do by I compute in by MATLAB, sir.
Yeah.
Yeah,
Okay.
I have the matrix A here
Mm-hmm.
and B. I change it
Mm-hmm.
to column and I do the CM matrix, the
Mm-hmm.
capability matrix, and I got something like this.
Mm-hmm.
And I calculate the that,
Mm-hmm.
and it's equal to -1.
Mm-hmm.
So the rank equal to 3.
Yeah.
The rank of CM.
Rank 3.
This is all I got.
Yeah.
Okay.
But I think the better way you can, if you remember, still remember, you can calculate CM here by using the controllable matrix of B, A and B.
Okay.
You still remember that? You can use MATLAB command CTRB.
Okay.
CT
CT
CTR B.
B.
Open bracket A prime B. A matrix A.
This one.
Yeah. A prime B and B. A,
This one.
no, it's not prime, not prime. Semi column.
This one.
No, not this column. Yes. Now, enter. Okay.
Okay.
You see,
Okay. Thank you, sir.
and you can check the rank of CM rank. No,
Yeah.
put
CM,
rank.
sir.
Yeah, CM. Okay, and you see, if
Okay.
you MATLAB. Okay.
Okay. It's
Now-
better.
Sir,
Yeah.
just do it by hand and please check it on the Salo group.
Okay. 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 So this is okay. I'm not sure yet because um I hope it's correct. I think. Okay, let me check with the MATLAB. Okay. So this is the S plus 10s squared plus 5s plus 2. Yes. Yes. So this is and it's correct, I think.
Okay. Thank you, sir.
Okay. Everyone can look at this at the answers of this problem. How about other, please? Do you have any other idea? Or do you have any difficulty? I hope that's no problem with you for this example. Okay. I hope that you have no problem at all. Okay. So now please look back to your slide and proceed with this example 3.2. And because you practice on this, so I think that there's nothing difficult for you for the example, and you can find example. But I will use it for illustrating MATLAB code. So I will explain this a little bit, and then we will use the MATLAB code for this. Okay. So assume that we have another problem with A equal to this, B equal to this. You're familiar with this. It is quite similar to before. And with the desired location is this. And okay. And okay, to have three position, and you have the S1, S2, S3. Okay. And we do exactly the same. We check with the continuity matrix, and we got the rank is 3, and then we take the characteristic equation for this, and you find this one, and you find that A2, A1, A2 is 6, A1 is 5, and A0 is 1. And also we can using this and 5 the characteristic equation for the pole, and we got this one, and we compare exactly by a couple of a alpha naught, A naught, alpha 1, A1, and alpha 2, A2. Then we got this one. This is a solution. For this problem, you have all in your slides. And for the MATLAB code, you can find you can show pole placement problem using Ackermann or placed. This is command. We are Acker or placed. Okay. So how can we do that? We can use this. You see, this is the first command to design this to find the gain matrix K. Okay, or you can use placed. Okay, this is the name of the scientists who invent this method. Okay, or you can use placed is same. Okay, but first we have to specify A matrix, B matrix, and then this is the Z matrix. The Z matrix is location. Okay, so we can put Z in this form and find the solution. Okay, so the command is Acker or placed. Okay, so for example, in this example, you can in this example here. So we see this is a matrix A. You got it in your slide. Okay, matrix A, B, and this is A matrix should be cover all of this. Okay, so you can declare A, B, Z in this form, and you can find the solution of K by using a command or using placed. They are look quite similar. Okay, but one is just have no decimal point number, and in here you see that we see the solution have a decimal point for specific K, because we got no number, no digit after the decimal point. Now practice a little bit. You can okay, put this on the computer and check this. And before I go further, I would like to ask you the questions. Do any one of you have the course after my course? Do you have any class after my class? If nobody busy with it, I will go further a little bit if you agree, because I give the lecture late. Or do any one of you have the problem if I would like to proceed with the new lectures a little bit?
No, sir. No problem.
Okay. If you have any question, sorry, if you have any problem with this, please let me know. Okay, I don't like to make it difficult for you. Okay. Okay, so you see that this is the MATLAB code for placement problem. pole placement problem. Okay, and you see that is very easy. And now we will see that another problem for the pole placement. And now we will consider the practical problem. Okay, in here. And we have to design the controller using the pole placement problem and investigate some situation it could happen with the system. Okay, and we'll consider these problems through an example 3.3 in my slide. Okay, now we look at the example. We have this is a magnetic ball suspension system. Assume that we have the metal ball here. Okay, and assume that we have the electrical magnet here, and we put here the current to here. And now we would like to control the position of the metal ball here. Okay, we know that when we put the current into the electrical magnet here, then this magnet will attract the metal ball. Okay, we introduce a force like this. Okay, and then and also the ball have the gravity force like this, and if we balance between the attract forces and the gravity forces, then the ball will be at any position we want, any position X we want. Okay, so this is an application, and you see that nowadays this principle is also applicable for some devices. You can find this in the market. In some cases, it's the inverse problem. You can not just make the problem like this. Also, you can inverse problem when the ball is above the magnet, electrical magnet. So you can push something off of the ground, okay, without anything in between, okay. But this is also the very good example to see how to make a controller for this problem. Okay, now the system can be described by this equation. Okay, so this is a dynamic equation for this problem, and in this case, you see that X is the ball position when we measure from the magnet, the position of magnet, and to the center point of the, and maybe it's not center point. I have to make it better. It could be here of the metal ball. Okay, and V is input voltage measured by volts, and IT is the winding current, and R is the winding resistance, and I assume that is 1 ohm. L is winding induction, and we assume that equal to 0.01 Henry. And M is the ball mass, and we assume that is 1 kilogram, and K is proportional constant, this here. And Z is the gravitation acceleration, and you already know that it equal to this. Okay, so we describe the system by this equation. Okay, so this is the electrical equation, and here is the mechanical part of this. Okay, we present all of this by very simple, I think, equation like this. Okay, and we can define the state variable for this system, and we define this in 3 variables. The first one, x1, is x, meaning that is the position of the ball. Okay, and the next is xt, x2t here, x2t here. x2t is dx over dt, meaning that this is a velocity, okay, and x3 is it, is the current, okay. So we have three state variables. Of course, you can choose another, okay. It depends on the how you would control this kind of system. And if you choose the state variable like this, then we got this equation. Okay, just replaced x by x1, x2, and x3 like this. Okay. So this is a equation like this, and now you rewrite this equation in form just replaced k. We got k. This is a constant. Or all of these can be considered constant. So we have k, m, z, r, and l. Okay, already here. The parameters, this all is parameter. We have all of this. Okay, so we just substitute a z, k, m, l, r, l there. Then we got this, and of course this is classical one. Okay, and this is we only put a and b, and no c, and no d, because c is depends on how many state variables we can measure. Okay. Okay. So just replaced the parameter, then we got this one, and we so there's a problem is this explanation of the system, and now the questions. You have to find the eigenvalues, transfer function, controllability matrix of the system, and the question is the system controllable? Is the system observable for y is ball position? Okay, if y is only xt is the ball position. Okay, and the system is controllable if yt is all velocity. Okay, meaning that like this. And how about the situation when yt is winding current, or yt is only it? Okay, and the last is that you have to find a controller to regulate the current of the electromagnet so that the ball will be suspended at the fixed distance from the end of the magnet. Okay, so this is some question that we have to solve, or we have to answer. Okay, so we will start from this. You have the eigenvalues, and okay, you know how to find eigenvalues. Okay, so this is the way we do that, and this is something we got, and we got, see here, we got one eigenvalues, and also you have to remember that eigenvalue are the poles. Okay, and here we got also this, and here we got this. Okay, so the problem is we got one pole at the right half planes, or in the right hand side of the complex planes. This means that, okay, the system is unstable. Okay, you already, I think that you already know that, because this system is, if we got three of them, like there's a system like we got three of them and three pole, but this pole is distinct pole. Okay, so you can represent the system in I think in this time domain xt equal like c1 is, okay, so this is s1 t plus C2 as 2T and C3 as CT. Okay. So in case, in the first two case, so this is S, you have put here, this minus here, minus 100 minus 8, but we got here a positive. Okay, this is positive one. So problem is that if T increased, okay, so if T increased, the output also increased. The distance X will be increases. Then it increases up to the ball hit the ground. Okay, so it's normal. The system is unstable. So this is a this is covered in this text paragraph. Without control, the steel ball would be attracted back. Okay, so two cases. If you put here too much without controls, if you put I here too much, then the ball will be attracted by the magnitude. Or if I is small, then the ball will hit to the ground. Okay, without control, without automatic control. So this is something. This is lateral. Okay, this is a expected. This is a system unstable. Okay, we have maybe two cases could be happen. The ball is attracted by the electromagnet or electrical magnet, or okay, hit the ground, fall down to the ground. Okay, so now first, in the first question, in the next question, we have to consider that we have only xt is output yt. Okay, so we see that we got c equal, okay, y equals cx, and remember equals c, x have 3, x, okay, x distance, x dot, and I, okay, because this is x1, x2, and x3. And now I assume that we have only x only, so will be c will be 1, 0, 0. X, okay, x dot, and I. Okay. So we assume that, and here is c, and we calculate the transfer function like this. This is the next questions. In the next questions, you have to find the transfer function. Okay, so we by this function we got here, and we got continuability matrix is this, and the rank is 3, and we conclude that okay, system is completely controllable. Okay, it's normal. Yeah, all know about it. Okay, but now we have to design the controller that will keep the ball as a location that we expect. And this is not output feedback problem, but here is a state feedback problem. So for state feedback problem, you have to measure all state. Okay, not in this case, you see the output only x, meaning missing two of them, missing the velocity and we are also missing the currents. Okay, so the first, so we're missing two, so we have to, if we would like to design the state feedback problem, okay, or controller, state feedback controller, then we have to measure all. But in case we cannot measure all, you have to design observer for this. Okay, but the next question is, can we observe all before we design observer? The question will arise that whether or not you can design observer for this. Okay, So the first question should be answered is that we check the observability of the system. Okay. Now looks. Okay. Okay. In the case number one, we has YT is ball position, and of course I explain CE like this. And now you can use check observability matrix and apply this. You already know how to check with this. And in this case, we check the rank, and the rank is 3, meaning that, okay, you can measure only the distance of the ball compared to the bottom end of the electromagnet. Then the system can be, the old state can be observed. Okay, so this is the first case. In the second case, we assume that we not measures the distance, but we measure the velocity of the ball and see what happens. Okay. Okay, so in this case, see that you got C again, output Y equals C, X, and equals C. Again, you got this already, X dot and Y. And in this case, you see that we measure X dot, meaning that we got C is 0, 1, 0 of X dot and I. Okay, so that's the reason why C have this form, and you have C form, you have to specify C, CA, and it's a square, and got this one, and still the rank number 3. So the system is completely observable. Okay, now we check for the last case when we measure only the currents. Okay, of course, when we measure only current, so the CE like this. And we check for the observability matrix, and when we check this, the rank, you see, the rank is only 1. Then the system is unobservable. Okay. The physical interpretation is that if we choose the current IT as the measures output, we would not be able to reconstruct the state variables from the measure information. In other words, you cannot design observer if you have only, you still remember observer? Okay, we have the system in the output of the system like this. Okay, so this is your system, and I assume that is a system S. This is the output Y, and you measure and you design observer here. Okay, and we denoted by Ulenberger observer, and then also the output, and this output is Y hat, and we compare with the output Y, and here we got, sorry, this is not L, the L here. Okay, and we got L here, so okay, plus. Okay. So and this is also input use. This is also the system estimate system, and you see that in this case you can observe, you can contract observe for other for missing state variables, but if the output here only the currents, it's impossible. Okay. So that's the reason why we have to check before we design anything. Okay, so this is the idea for how to do this, but it better is for this example, you can investigate the problem using the MATLAB, because we would like to draw also the figure of the output. Okay, the figures of the output of the response for the system. And you know how to do that. You just put the system in this form. Okay, you already know have this form, but in this case, we so use that the equation is linearized about the equilibrium point. Okay, and we assume that the system may be a linear one, but we assume that around the equilibrium point, the system is linear, because I said from the beginning of the course, in this system, we do not consider the nonlinear case. So to decide anything, you need to specify the system in a linear case. But I don't know, I don't show you how to linearize the systems around the equilibrium point. You can find this on the books, because we do not consider the nonlinear case. If you take the nonlinear case, I can show you several ways to linearize the system based on the equilibrium point. Okay, the idea is this: if we got something like the nonlinear curve like this, you can assume that you are working on, for example, working on this range. Okay, and then you can linearize. This is the equilibrium point, and you can linearize, replace the curve here with a straight line through the equilibrium point. Okay, so you see that this is one way to approximate the nonlinear system by a linear system. And maybe we got another consideration. When we move to another, you can assume that this is also linear. So we apply this, meaning that we can apply the linear theory for the nonlinear system. It's not always perfect, but sometimes the system working on very small range like this. Then, or you can move from this equilibrium point to another equilibrium point, then we apply this, will be okay. But again, this is not topic for this course. So I just show you the solution to investigate the system, not to explain why, or not go into details. Okay, so if you attend some other course in when we call this graduate course, you will learn this, okay, in this course. But in undergraduate level, we never talk about this, because this is a very complicated one. All the theory we learned so far cannot apply for the nonlinear case. Okay, it's wrong. Okay. So this is we assume that we got these models by linearization, and if we do not working on this distance, for example, 0.7 or 0.3, meaning that you got the new equilibrium point, then you may got the difference system matrix and system input matrix. Okay, but here we assume that working on this, and I show you we are working on this point or this point. Okay, so you can linearize in this point only. Then we got this matrices. So you know how to control or how to use this. So we will assume that we can put it into MATLAB and using eigenvalues to find the pole, and the pole is here, and one pole still positive. Okay, and then you can change the system. This is another way we can look to the open loop system. Okay. Okay, and here we explain more. This is the pole in one pole in the one of the pole is in the right half plane. Then the open loop is unstable, and now we can use the MATLAB code to observe what happened to this unstable system. Okay, and in case you have non-zero initial condition. Okay, you can we can make a system like this, and this is the initial x naught, and we observe. This is time of observe. Okay, and we have no input. Yeah, so we have the linear simulation of the system with the input used t and initial condition. This is a the MATLAB command that you can use. Okay, and then we will see that this is the function yt, and this is with the also this other output parameter. Okay, again, you can if you don't know this, you can use help. Okay, linear simulation of this. Okay, and enters MATLAB will help you to see this. What I try to show you here is just to investigate the system using the MATLAB codes to understand more about the system. And you see, this is the output, ball position, and you see that it starts from 0, but now it move up like this very quickly. Okay. You see that it looks like the distance between the ball and the electromagnet also go to infinity. Okay, this means that the ball hits the table or floor first. Okay, and of course this go out the equilibrium point. We not assume that. Okay, but in this case, you see the system is unstable. Okay. Okay, so this, okay, I think that I just remind you about you can check the range, the controllable controllability matrix and check the rank. You have the rank here, then of the system, and you have the system AB, and to check that the rank is 3. So this system is completely controllable, and also the observable. We can observe this. Okay. Okay. After that, you can find the state feedback gain K. Okay. And of course, in this, we assume that we can observe all of this pole. Okay. So first, we assume that, okay, you can check with the, you can try with the any pole you want, and I assume that I use pole number 1, number 2, number 3. Okay, 3 poles. Okay, and we would like to place this this system AB and this position. Okay, this K, and now you see that we have the system closed loop system. We close the system with a SS display, and now we have A minus BK, and we have SS. You have to put for SS command. You have to put A, B, C, and D. Okay, but D in this case D equals 0. And A is now a closed loop system, meaning that we include the controller K into the system. Yeah. If you forgot this, please come back to my slide, and we got this in the observer design section. Okay, you put the number K no, sorry, in the state feedback control. okay, section, I got a figure about it, and you can find this form of A in there. Okay, and then when we have this, we have also linearize the system, a closed loop system a little bit, and then we will see that the system now look like this. Okay, and you see that this is the equilibrium point, and then it go to the where we want. Okay, so the system look like this. Okay, this is the response. Okay, this is the difference between the what we want and the output. So this is always 0, but meaning that the state variable go to the location we want. Okay, but of course in this case, you see that you can see that this is a overshoot. Okay, and you see this is too large, but it could be not too large. Okay, it could be too large like this, and even you see that it's still large because maybe it's small, but you see that this is metal ball. So if we have too large overshoot, then the ball will oscillate a little bit. So if you would like to reduce this, we will check with another pole. Okay, so this is the first. This is the first test. Okay, and the first try, and you can do the second try. Okay, like this. Okay, in this case, in the first case, we have in the half plane we got okay. In the range is -10, and in the emergent pass also 10s. Okay, so we have P1 here and P1, P2 here, and also P3 here in the first try. Okay, 10, 10, 15, 50. Okay, have 3 pole. Okay, the real part is 10, the emergent part is also 10, and one have no emergent parts, meaning that it's light in the real. Okay, now because the overshoot, I think that is maybe too large, so we move this to here. Sorry, to here because the emergent pass also 20, so 20 here. So we have P1 here, and also P2 move to here, and P3 is now 100 minus 100. See here. Okay, we do exactly the same, and you see that it could be like this. It's still large, okay, but it faster, a little bit faster, and you see it's like this. In the first test, first try, like this, and now it's like this. But I think that this should be carefully checked with this. Maybe I have to swap two this. I want to check because you already know that when we move the pole to this, the system becomes slower. The response becomes slower. Please check for me with this. Okay, I will check again because in general when we move the pole to the left hand side, the response of the system, the output will be slower. Okay, when we move it to the right hand side, up until or very close to the emergent path, then the response, the output will be faster, but it more oscillate will be introduced some oscillation, and also the system more into the unstable region, because you know this is a stable region and this is a unstable region here. We cannot put the system, the pole here. Okay, this is unstable region, but very close to the unstable region, meaning that we introduce more oscillation and the system more sensitive. Okay, it will be very easy to fall down to the unstable region. So that reason why we try to move it to the left-hand side. But if we move it to the left-hand side too fast, then the system become very slow. For example, like this. Okay, this is, we expect, but if we move to the left too much, then it quite slow like this. If you put it to the right like this, then the system could be like this. It's very quick to get the first expectation point, but then it introduce overshoot and then some oscillation like this. Okay, or even it lies in a better way and in a better situation, it could be like this compared to the K like this. Okay, so I hope that you will check with this for me at home and try to test the system with this code. Okay, it's not difficult and it easy to understand, but you have to check with you for some command like the linear simulation like this, or okay, SS. I hope that I introduced SS for you before. Okay. 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 Do we have any question so far?
No.
No. Everything okay?
Yes, it's okay.
Okay.
Okay. Okay. Good. So remember, up to this point, I finished. I finished chapter 4. Okay. Then we got one chapter left, and if possible, I will introduce one more chapter about the computer control based. Okay, computer based control, and of course, this is related to digital control problem. But we have one chapter left in the chapter 5. And now we will move, in my next lecture, we will move to the next chapter. And this chapter talk about discuss about optimal controls of dynamic system, and it related to some other thing. And this is a optimization problem, and we got something else to do with. So please read this at home before we go to class. Next week we'll have an offline class. Do you all know that?
Yes. Yes.
Okay, good. And, sorry,
No.
you all know?
Oh, I know.
Yes, it's good because okay. So actually, I try to delay the process exams because I don't like to do that online, and I hope that the next week we will gather in TNUT, but I'm not sure, so I try to postpone this because before this week I'm not sure. I just guessed, so I intend to give you the progress exam, but I think that we'll soon gather in our university, so I delay this. But of course, you know that it's a little bit late because I hope that we have 2 weeks left. 2 weeks left for the lectures. I think. I'm not sure yet, but I think that 2 or 3 left. Yeah. Okay, I will check this. Okay, because we have the old schedule, but if I remember correctly, we'll have 2 weeks left. Okay, or maybe shorter. I don't know, but I try to finish the next chapter in 2 weeks. And also we got some exams. At least we have 2 exams or 2 or 3. Okay. So do you have any more questions?
No, sir.
Okay, and also we have we still have 2 absent today. Do you know who absent today?
No.
If you know, I will don't need to
Okay.
check. Okay. How about Mr. Nguyễn Nam Hưng? I hope no, because we have 3 left. Do you know how who absent today?
No, sir.
No.
Of
Okay.
course,
So
this is a Mr. Nguyễn Nam Hưng is
yes.
always
Yeah.
missing.
Yeah. So I have to check the Bùi Thái Anh, please. Bùi Thái Anh. Okay, you are here. I saw you.
I'm here. Yeah,
Okay,
sorry.
Nguyễn Quang Anh.
Yes, I'm here.
Okay, Phạm Tuấn Anh.
Yes, I'm here.
Văn Đức Chiến.
I'm here.
Okay, Phạm Bá Cương. Phạm Bá Cương. Okay. Nguyễn Việt Cường.
Here, sir.
Okay. Tạ Mạnh Cường.
Here, sir.
Okay. Đặng Thùy Dương. Okay, you're here. Lê Quang Đạt.
Yes, I'm here.
Okay. Đỗ Văn Đức. Check. Okay. Nguyễn Thế Đức.
I'm here, sir.
Okay. Nguyễn Văn Hà.
Yes, I'm here.
Okay. Vũ Thanh Hải.
Yes, I'm here.
Okay. Thank you. Đặng Thị Minh Hiền.
Yes.
Okay. Nguyễn Thị Thu Hiền. Okay.
I'm here.
Sorry, here. Bàn Phúc Hiếu.
Yes, sir.
Okay. Hoàng Văn Hiếu.
I'm here, sir.
Okay. Lương Công Hiếu.
Yeah,
Okay. See. Phan Trung Hiếu.
Yes, sir. I'm here.
Okay, you're here. Trần Đức Hiếu. Trần Đức Hiếu. You're not here. Trần Đức Hiếu. Again, Trần Đức Hiếu, please. Are you here? No?
He not here.
You're not here. Okay. So, thank you very much. I found who absent today, and for others, he is not absent. Okay. So again, do you have any more questions, please?
No, sir.
No, sir.
Okay. You have no question. I would like to finish my lecture today here. Thank you very much, and see you again
sir.
in
Yes, sir.
TNUT.
Sure.
Okay. Okay. Thank you.